Good morning, everyone. Welcome to the CTBUH Toronto chapter webinar on seismic performance and of modular steel building. A little bit of housekeeping before introducing our speakers. The Council of Tall Building and Urban Habitat, CTBUH, is the world's leading non-profit organization for all those interested in the future of cities. It explores how increased urban density and vertical growth can support more sustainable and healthy cities, especially in the face of massive urbanization and increasing effect of climate change worldwide. The relationship between policy, buildings, people, urban density, urban space, interior space, and infrastructure is key. Founded in USA in 1969, the CTBUH member network embraced more than 650 companies in over 100 countries, with over 1 million of professionals working in the building industry sectors. Now, let me introduce today's speaker. Amir Fatih is a structural engineer at Dialogues Toronto studio. Amir brings comprehensive knowledge of design and construction processes of steel and reinforced concrete structure based on Canadian codes to his project. He has extensive knowledge of construction management with regards to the PMBOK guide and standards. Amir specialized in reinforced concrete structures, steel structure, high-rise design, modular steel building, seismic dynamic and analysis retrofitting, masonry structure and numerical modeling. Amir research has been published in a number of publications and was awarded a research grant from the Natural Science and Engineering Research Council of Canada for his work into the dynamic behavior of modular steel building. Next, Rafaela Sanchez. Rafaela's PhD research involves numerical and experimental investigation on intermodular connection for better understanding and modeling of seismic behavior of modular steel building. Rafaela earned her bachelor degree in civil engineering in 2007 and worked as a project manager and bidder for 6 years in a steel structure manufacturer in Brazil. In 2015, she earned her master's degree in civil engineering from the Federal University of Rio de Janeiro and started her PhD program in structural engineering at the University of Toronto. Now I leave the floor to Amir and Rafaela, but please hold your question until the end. Thank you.
Thank you, Daniel. And hi, everyone. My name is Amir Fatih. And as Daniel mentioned, I'm a structural engineer at Dialogue, working with a great team on different projects from industrial to residential, high rises and low rises. I joined Professor Merjan's team in 2010 at the University of Toronto to continue my postgraduate studies in structural dynamics and earthquake engineering. During my master's, as you might guess, my research was mostly focused on the dynamic analysis of modular steel buildings. Unfortunately, at that time, there wasn't many researchers or resources on the dynamic behavior of modular buildings, except maybe a few technical papers and a few limited studies on seismic behavior of low-rise modular buildings. So we started our investigation on modular steel buildings, or MSBs, in 2010 that I will briefly mention some of the topics to you later today. But before I do so, I'm gonna quickly explain to you what I mean by modular buildings. What does it mean when I say modular construction, and what differentiates modular construction from traditional or conventional constructions? After these introductions, I'm gonna have my colleague Rafaela to continue with more details on our research and our recent studies. Modular buildings are basically the result of modular method of construction. And other than that, they follow the same codes and standards and use the same materials and designs as conventional buildings. But on the other hand, they have different detailing requirements that differentiate the final product, which is the modular building, from the conventional or regular building. The main differences that you may all know is that these buildings are usually made from volumetric units. Most of the time, they are complete, fully finished modules that are built in a remote facility. Then these six-sided modules would be transferred to the site to be assembled beside each other or on top of each other to create an entire building. And as you can guess, this would significantly reduce the overall construction time. And since the units are made in a factory setting, there would be a huge saving in material waste. There are some common misconceptions about modular buildings, like some people might think of modular buildings as ugly-looking gray boxes, temporary structures, inflexible or restrictive in design, or that they are basically substandard accommodations. But as you can see in this photo, this is a recent project in the US, 469 Dean Street in New York, Brooklyn. It has 2 underground levels and 32 stories above grade, and is one of the tallest volumetric modular apartment in the world. As you can see in the right photo, inside the unit is almost identical to our conventional high-end condos or apartments, and there's no major differences in layout or unit dimensions. Also, there is another project, the new Marriott Hotel in Manhattan, New York, which is currently under construction. This is a $65 million project with 168 rooms, 26 stories height, and it's located at 842 6th Avenue, which will be one of the world's tallest modular hotel. And in this project, each steel module contains one fully outfitted guest room, which is pre-painted, decorated, outfitted with beds, beddings, floorings, and even toiletries. The hotel's roof and rooftop bar are also concepted using modular construction. Generally, modular buildings are categorized into 2 types: 2D panelized systems or 3D volumetric systems. In 2D panelized systems, they basically divide the modules into 2 vertical and horizontal elements, and they pack everything and stack everything on top of each other and send them to the site. And usually this is more time consuming when it goes to the site for assembly, whereas the 3D volumetric system is more pre-finished off-site. And they often have all the plumbing, electrical work, mechanical work already included. And in some cases, like what I've shown you in a Marriott Hotel case, they even have the furniture and decoration already packed inside the unit, and they send everything together as a package to the site. Now, by having these prefabricated formations, I would say, we would get a relatively different structural system in terms of how the forces and loads are being transferred throughout the building in both vertical and horizontal direction. In terms of load transfer mechanisms, for gravity, modular buildings are generally classified as either a load-bearing wall system, as shown on the photo on the left, or a corner supported frame, as shown on the photo on the right. And as for the lateral load resisting system or seismic force resisting system, we have either steel bracings or concrete or steel shear walls and core, which is pretty much similar to what we have for regular buildings. Now, to transfer these lateral and vertical loads between the modules, we need to add and design an additional intermediate element in between the floors and ceilings and in between the modules in horizontal direction. And these connections were one of the things that we looked at in our previous studies. In those studies, we looked at the structural details, connections, and individual elements, as well as the overall nonlinear behavior of the modular steel building. In terms of details, we used OpenSeas, which is an open source seismic design software. We looked at the relative displacement and rotations between the modules. Because unlike the conventional buildings, there's no single uniform diaphragm at each level, and we have multiple rigid diaphragm that are connected together per level. We've also investigated the way that the forces are transferred through the columns and horizontal connections where the modules are connected to each other, and we studied the additional concentration of inelasticity at those joints. And in another study, we used 3D pushover analysis and 3D incremental dynamic analysis, or IDA, to better understand the overall nonlinear dynamic behavior and characteristics of the modular buildings. In our current study, we moved a few steps further and investigated the other code-related properties of modular steel buildings and the dynamic behavior of high-rise modular buildings that my friend and colleague Rafaela will explain to you shortly. I'm just gonna stop sharing here so she can share a screen.
Hello, everyone. I'm Rafaela here. So let me just share my screen. Where is it? I think it's this one. Let's share. And I guess this is the, so I hope you can all see my screen now. And yeah, so I joined Professor Merjan's, I'm a civil engineer, as Danielle said, and I joined Professor Merjan's research group in 2015 when I started my PhD program, which I intend to finish this fall. And I've been working on modular construction, in particular modular steel buildings, since 2016, mid-2017, continuing previous work done by other graduate students from our research group, such as Amir's work. My thesis is focused on new type of connection for modular steel buildings. But for today's presentation, I prepared a few slides so we can discuss some details of our research project that was conducted in collaboration with Dialogue. And this project was recently published in the Engineering Structures Journal. And the title you can see on the screen is Investigation of the Seismic Performance of Braced Low, Mid, and High-Rise Modular Steel Building Prototypes. And for this paper, all the four of us are the authors. So there's also Junji, his PhD candidate, also supervised by Professor Merjan in the Civil Engineering Department at University of Toronto. But before we start discussing the paper itself, I would like to share with you a graph that I prepared that shows the change in height of modular buildings over the years, and also the number of modular buildings around the world. So I prepared this graph which is a compilation of these 4 studies here below. And you can see that the axis here on the left is the building's height in stories, number of stories. And with the blue bars, the tallest building finished in that particular year. So we can see there is a clear trend increasing the height of modular buildings. And on the left side is the number of buildings finished around the world. And this dashed red line is the cumulative number of buildings. So we can see that especially in the past 10 years, maybe 8 years, we have a clear increase both in number of modular buildings and also their heights. So we're building more and we're building higher. And despite of that, the number of studies on the dynamic behavior, more specifically the seismic behavior of modular buildings, is still quite limited. So with that in mind, Dialogue and UFT created this partnership, and to investigate by a numerical study, to investigate the seismic behavior of low to high-rise modular steel buildings, or MSBs, under different hazard levels. For that purpose, we selected 3 building prototypes, selected a 6-story, 12-story, and a 32-story MSB. So we have a low, a mid, and a high-rise. And we performed nonlinear static analysis, or pushover, and also bidirectional nonlinear time history analysis. So this means that we have 3D models, and we are applying ground acceleration in both orthogonal directions simultaneously. And the main parameters of interest are the overstrength and ductility seismic design factors, which are determined in the design code. And we wanted to investigate if these design factors change as we change the building's height, because this was pointed out by other authors. And so we wanted to see if that's the same for modular buildings. We wanted to take a look at the interstor drift, the maximum interstor drift, and how it's associated with structural damage. Of course, in the paper, we have a lot more results, but for this presentation, I selected this as I think these are the most important ones. So for all 3 buildings, we considered the same plan view, which was provided by Dialogue team. And the footprint is 31.9 per 22.8 meters. This is all in meters. And so in total, we have 727 square meters. So they provided us the architectural plan. And with that, we assigned the location of the modules. So each one of these rectangles here is one module. And so, for example, we put these 3 modules together, and this creates an area for a 2-bedroom apartment, for example. And so we have a 2-bedroom, 1-bedroom, another 2-bedroom, another 2-bedroom, 1-bedroom, and even a 3-bedroom. We also consider the location of the corridors, which are these shaded areas here, and the entrances to the units, which are these red arrows here. We also consider the location of the staircase and the elevators. So this is pretty realistic plan view. And we have in total 18 modules per floor. It doesn't necessarily mean that we have 18 different modules, right? We can combine, for example, this module number 1 and module number 17. They're probably going to be very similar. So that improves the efficiency of the construction. And the module's dimensions are shown here on the right, and it's limited mostly because of transportation requirements. So we had to take that into consideration, and we defined that the height of the modules is all the same for all the modules, 3.5 meters. The width of the modules varied between 2.7 meters and 5 meters, and the length also varies between 8.8 meters and 12 meters. So with that plan view, we define our seismic force resisting system, which is a braced system, purely braced, and we define the location of these braces based on the corridors and to avoid doors, to avoid windows. So we designed the building for moderate ductility according to Canadian code and following the capacity design strategy, where the braces are expected to experience the inelastic deformation and the other structural elements such as columns and beams are going to be preserved. So here we can see the location of the braces for all the three buildings. So these two black symbols here, the X, black is the X brace, and the black chevron symbol is the chevron brace. So for the 6th story, we have chevron braces in this locations here, and X braces here, here, and here, here, and here. But when we change to the 12th story, we realize that these X braces here would increase too much the load in the columns. So we changed for the 12th story and also for the 32nd story, we changed to all chevron braces to save a little bit of in the columns. So for the 12 stories, this gray symbol here, so they're all located here to resist the lateral loads in the X direction. And we have 2 here and 2 here and here to resist the loads in the Y direction. And for the 32 story, we had to include a little bit more braces here because of the increased lateral load. And we also had to, in the first stories up from the 1st all the way to the 18th floor, if I'm not mistaken, we had to include more columns. So we can see, for example, here we have a cluster of columns at the lower stories. This is to take into account the increased brace-induced forces and also gravity forces for the 32-story building. So another thing is that we consider the braces within the module. So we don't have an external concrete core or steel frame core to resist lateral load. And this is expected, this approach is expected to expedite even more the assembly on site. So that was the plan view, and these are some elevations just to illustrate this distribution of the braces. So as I said, for the 6th story in the Y direction, we had X braces, right? And these are the heights of the buildings in meters. And for the 12th story, we have, and for the 32 story, we have all chevron braces. And this is in X direction, this here is in the Y direction. And for the 32, I'm just showing the X direction because the Y direction, it's very similar to what we did in the 12th story. So it looks pretty much like this as well. But here we can see that in the first stories, we have an increased number of columns, as I explained before. So all these 3 buildings we modeled in ETABS Ultimate. And now we're gonna discuss a little bit how we model these. So this is a schematic representation of the model. We considered frame elements for all structural members, for braces, beams, columns, everything's frame elements. We also consider individual diaphragms for all the slabs, ceiling and floor. Here on the left, we have a representation of what will be 2 modules on top of each other. So this will be the upper module, this will be the lower module. And we consider lumped plasticity. So in the middle of the brace, we assigned a automatic hinge, which is a feature in ETABS that is defined based on ASE 4117. And for the brace, it will be an axial hinge, which is shown here. On the right side is a representation of how the force displacement relationship of this axial hinge would look like. So we have, for example, these green dots are the yielding capacity of the brace in tension and buckling of the brace in compression. We have these blue dots are the ultimate capacity. The pink dot is the residual strength, and the red dot indicates failure of that element, the brace indicates. So other than the brace, we also assigned a flexural hinge in the middle of the ceiling beam. Even though the ceiling beam is not expected to develop any plasticity, but yet we assign this hinge there because in the post-processing it's easier to visualize if that beam had its moment capacity exceeded or not. It's not expected to, but we just put it there just so it's easier to check. And we also assigned a PMM hinge, which is axial biaxial moment hinge in both ends of all the columns. So here, this image here in the middle is again a schematic representation of the intermodular connection, how we modeled it. So for the beam column connection area, we consider this rigid elements, which is to account for the increased stiffness of the connection region. We considered a pin end in both ends of all the beams and also all the braces. So our seismic force resistance system is purely a brace system. And we also considered a pin end in the columns. That model was proposed by another author, and that is to take into account potential relative rotation between the upper and the lower column, because assuming that this vertical connection is welded, and once we place one module beside the other, we may not have access to weld all around the column, and that could lead to an increased relative rotation between columns. So to take that into account, this connection model is proposed by this author, and we're just following the same approach. So now about the analysis that we conducted. So as I said, we did pushover and nonlinear static and nonlinear dynamic. So for the nonlinear static and also model analysis, and so for the model analysis, we did a 3D model analysis, and also we had to run what we call the 2D model analysis, even though the model is still 3D model, but we conducted the model analysis in X direction and also in the Y direction. So we could find the first period in the X direction, which we're calling here T1X, and the first period in the Y direction, which we call here T1Y. So with these three parameters are important for the ground motion scaling procedure, which I'm going to discuss in the next slide. And so for the pushover, we also did the pushover in the X direction and Y direction separately. So we could use the pushover curves to estimate what's the ductility and what's the overstrength of our buildings. So we use the displacement distribution according to the first mode shape, obviously in X and Y direction. And we obtain the pushover curve. And with this curve, we can find what's the max roof displacement and what's the yield displacement, which is associated with the first hinge formation. And the ratio between the max displacement and the yield displacement is what we call the ductility factor, or RD. And in the same way, we can find what's the max base shear and what's the design base shear. And the ratio between these two is what we call in here the overstrength factor, or RO. So now for the nonlinear time history analysis. So we did as I mentioned before, a bidirectional nonlinear time history analysis. This means that we selected 12 pairs of ground motion. So we have a two-component ground acceleration. One component we apply in the x direction, the other component we apply in the y direction simultaneously, right? And then we get the response of the building. So we selected 12 of these pairs, and we scale them to different hazard levels following FEMA P58 procedure. And we selected the 3 hazard levels. Actually, in the paper we have 4, but here I'm going to talk about only these 3 because I think they are the main ones for Vancouver. So we scale to FE, which is frequent earthquake hazard level, DBE, which is design-based earthquake, and MCE, which is maximum credible earthquake. So the intensity increases from FE to MCE. And here on the right, we have what will be the spectral acceleration for the city of Vancouver. And the red line will be for the MCE target, the blue solid line, the DBE, and the FE target is the green line here. Each one of these gray lines is one ground motion spectrum. And we scale using T prime. T prime is the average between the first mode in X and first mode in Y direction. That's why I had to run model analysis in these 2 directions. And we evaluated the match of this ground motion spectrum and the geomean within this period range here. So this is all in FEMA P58. Other than this, still about the nonlinear time history analysis, we ran a direct integration method. We considered the delta and large displacements, and we assigned 3% damping ratio using Rayleigh damping. But we also managed to reduce the total duration of the analysis by reducing the duration of the ground motion using the strong motion interval. And we did that by using Arias intensity. So Arias intensity is defined by this integral here, which is the integral of the time acceleration. And it's defined as the interval that accumulates between 5 and 95% of the accelerogram's total energy. And this is when the structural damage is expected to happen, right? And by doing that, in our case, we selected 5% and 98% just to be on the safe side. And with that, we were able to reduce the total duration of all the ground motions that we ran. And so in average, we reduced in 50% the duration of the ground motions, which allowed us to run a large number of analyses with a reasonable computational resources. So to finish the numerical analysis part, we, for each then pair of ground acceleration, we run the time history analysis, and one of the parameters that we were interested in was the interstory drifts, in particular max interstory drift, which is commonly used to establish the severity of the ground motion. And FEMA 356 determines 3 damage states for braced steel buildings that associates interstory drift, or ISD, with structural damage. So in FEMA, we have the damage states called immediate occupancy, or IO, and its limit is 0.5% interstory drift, and is associated with minor yielding or buckling in braces. We also have life safety damage state, or LS, and the limit is 1.5 interstory drift. It's associated with many braces yielding and buckling, so it's a more severe damage. And we also have the collapse prevention damage state, which is limited by 2% interstory drift, and it's associated with an extensive yielding, buckling of braces, and failure. So this is what we selected for analysis, just so to summarize the whole story up until now, we have 3 buildings, 6, 12, and 32 story modular brace steel building. We ran nonlinear static analysis or pushover and bidirectional nonlinear time history analysis with 12 ground motions scaled to 3 different hazard levels. And we're going to analyze mostly interstory drifts and ductility and overstrength factors. So going for the results part. So these are 2 pushover curves for the 12-story building. And the one in the left is in the X direction. The one on the right is on the Y direction. So as I was explaining, once we find what's the max displacement and what's the yield displacement, we can estimate what's the ductility factor of that building. So here I'm calling RDX because it's the ductility in X direction. And we can find what's the max base shear and what's the design base shear we already have. So the ratio between these two is our overstrength factor in the X direction. So similarly, if we do that for the Y, with the Y direction pushover curve, we can also find the ductility in Y direction, overstrength in the Y direction. In this case, they're quite similar. And if we do that for all 3 buildings, we can summarize this in this graph. So here on the left, we have the overstrength factor per building. So we have the 6-story, we have the 12-story, and we have the 32-story. And the blue bar is the excuse me, the X direction, and the orange bar is in the Y direction. Let me just sip some water here. And similarly, on the right side, we have a ductility factor per building. So again, we have 6 and 12 and 32-story building. The blue bar is the X direction. The orange bar is the Y direction. What we wanted to see here, what we were expecting to see here, and what we did see, was the reduction in the overstrength factor as we increase the height of the building. And same thing happened in ductility factor. As we increase the height of the building, we saw a tendency of decreasing these 2 seismic design factors. And this was observed also in other studies, and we observed the same thing in our study here. Now, moving to results of the nonlinear time history analysis. One of the results that we can evaluate here is the distribution of interstory drifts throughout the height and how much they vary. So very much I'm talking about the records to record variability. So for example, here on the left is the max interstory drift per floor. So this is first, second, third, and so on up until the 12th floor. Here in the X direction, here in the Y direction. For ground motions is scaled to FE hazard level, which is the less intense hazard level. And we can see, first of all, that each one of these gray lines is one ground motion. So we see that depending on the ground motion, we change quite a lot the response of the building. So that's why it's important to calculate the average, which is the dark line here, the thick black line here in the middle. And also similarly in Y direction, right? This is the same thing. And this dashed line here is the IO limit state. It's the immediate occupancy limit state defined by FEMA. And on the right side, you have the same idea, but these are the results obtained for the MC hazard level. So one thing that we can observe here is that we can see there's an increase in the variability of the response, right? If you compare MC and FE, in both directions. And obviously, we have an considerable increase in the interstory drift, right? So for example, while under FE hazard level, the interstory drifts are below IO, when we go to MC hazard level, the drifts start to get closer to collapse prevention limit state, right? Which is expected. But another thing that we want to see here is that if I take all the max, like let's take the worst case scenario from all this analysis here, let's take the max interstory drift per ground motion. So I'll take the max for each one of these gray lines. I'll take the max value, right? So for the 12-story under FE, the max was given by ground motion number 5, okay? The max of the ground motion number 5 is this one. For each ground motion will be a different one. For DBE, we can do the same. For MCE, again, we have for ground motion number 9, for example, we have this is the max. So if we take the max response per ground motion, per building, per hazard level, we can summarize this whole story with these 3 graphs here. So here again, we have these dash red line is the collapse prevention limit state. The dashed dot line here is the life safety. And this dashed black line here is the immediate occupancy limit state, right? And each one of these dots are the max interstory drift obtained for this particular building under a specific hazard level. So for example, the blue is FE hazard level. So for example, ground motion 1 scaled to FE hazard level. This was the max interstory drift. The orange is for DBE and the gray is for MC. So we did that for all 3 buildings. One thing that we can see here is that it's expected, but as we increase the intensity of the ground motion, the response in terms of drift tends to increase, right? This happens for all of them. And also, as we increase the height of the building, so we change from 6 to 12 and then to 32, we see that the max interstory drift tends to get closer to collapse prevention and exceed collapse prevention for the 32-story case, for example, right? So another way of evaluating this is that, let's say that I'll pick all these dots here, and then I'll calculate the average of the max interstory drift, right? And then I'll do that for each hazard level and for each building. And so when we do that, we have this super summarized graph, which shows the average max interstory drift here per hazard level. So the blue bar is FE, DB is the orange bar, and MC is the gray bar, and also per building, right? So when we do that, we can see that the 6-story building, which is our low modular building, it has a quite acceptable performance. Under MC hazard level, the average of the max interstory drift is still below life safety damage state, which is associated with a lot of braces yielding and buckling, right? When we go to the 12-story, we see that the average max ISD exceeds life safety damage state. And one other thing that we can see from this graph here is that all 3 buildings have a comparable performance when they are subjected to FE hazard level, frequent earthquake, which is less intense one. So all of them have their max, the average max ISD below IO. But this difference in performance starts to get more pronounced as we increase the intensity of the ground motion. So, for example, when we go to the 32-story, we see that the average max interstory drift, it exceeds collapse prevention damage state, which is associated with the extensive yielding buckling of braces and also failure, right? We can, so for example, if we compare the 3 gray bars, we see that the difference between them, it's much more than the difference between the 3 blue bars, right? So this suggests that perhaps high-rise modular buildings to be designed for areas of low seismic activity is probably okay, but for areas of high seismic activity, I think it requires a better, perhaps a better design strategy or better understanding on how it works. But to help us visualize in these damage states and how they are associated with the structural damage, I've selected a few images from ETABS generated by ETABS, where we can see those green dots, blue dots that show yielding, buckling, and alternate strength, and so on. And I've selected the output from the ground motion that led to higher response. So for example, the 6-story, so this is for the 6-story underground motion number 1, which was the one that led to higher response. So just so the difference in structural damage is more pronounced and we can see it better. So this is the structural damage at the end of the dynamic analysis. This one is ground motion 1, as I said, under scale to FE hazard level. So we can see that there's some braces here that start yielding or buckling. Some braces don't even see anything. And we have some here going to the residual strength range. And as we increase the intensity, as is expected, also the severity of the damage increases. So for a DBE hazard level, we see that several of the braces are in the residual strength range, and some of them are already failing. And for MC hazard level, we have a considerable amount of braces failing, and few of them are still in the residual strength, right? But still, all the damage is limited to the braces, which is what we were expecting to see. So for the 12-story building, I selected ground motion number 9. And the idea here is the same. We'll have the first here's ground motion 9 scale to FE hazard level. And we can see that we have several braces yielding, some of them not at all. We have some more in the residual strength limit. And as we increase the intensity of the ground motion, we see a more severe damage. So for the DBE, we have pretty much all of the braces in the residual strength stage. And when we go to the MC level, we see that even though the plastic hinges are mostly restricted to the braces, we still saw a plastic hinge forming here in the column, right? And last but not least, we have the damage state of the 32-story building. For this one, I selected ground motion number 6. And so as I was saying before, all 3 buildings for FE hazard level, they have a more or less same behavior. So see some braces yielding, some of them not seeing anything at all, some of them in the residual strength. So for FE, DBE hazard level, they're more or less comparable performance, right? But when we go to MCE hazard level, then the story is a bit different. The 32-story building, it developed a considerable number of hinges in the columns. So here I zoomed in just so it's easier for us to see. So these are braces failing, these are braces in the residual strength limit, but we see a non-negligible number of columns hinging here. And this is something that we don't want to see, right? So this suggests us that for we still have a lot of work to do when it comes to high-rise modular steel buildings. Still have to investigate more this and try to propose different approaches to improve this behavior, so we can continue to build tall modular buildings all over the world. So to conclude, I selected here a few topics that I judged to be more important. So we saw that both our ductility, seismic design factor, and overstrength factor, they both tend to decrease with increasing building's height. And in the code, these two factors are selected based on the type of the seismic force resistance system, not exactly on the height of it, even though there are some limitations there, but still mainly based on the type of the system, right? I'm not saying that the code is wrong. I'm just saying that there are few studies that are showing this tendency. And we also saw this in our modular buildings. Another thing that we saw is that the structural damage in low and mid-rise MSBs, meaning the 6 and the 12-story, tends to be limited to the braces, even though for the 12-story we did see some column hinge there, but as an overall tendency, it's usually limited to the braces. Now, for high-rise modular buildings, we saw a tendency for column hinging under severe earthquakes, and this tendency much more pronounced. And we also saw that the building may exceed collapse prevention limit state under MC hazard level. So we have, of course, this study is not the final one, right? We have to continue working on and improving it. So for future / ongoing works, we have the intermodular connection study, which, for example, what I am doing in my PhD research, right? To propose new methods of connecting these modules together to either improve the response or to make a faster assembly. We're also working on a better modeling or a more realistic modeling for the beam column brace connection, because in this study, we simplified the connection part by saying that, okay, all the beams are pin, all the braces are pin, and there are other ways of representing this connection. For example, to include the gusset plate or to make semi-rigid connections and things like that. This is something that we also look into. And also we are studying including supplemental dumping devices to improve the overall performance of these buildings. So that's what I have prepared for today. I would like to thank, I know that Philip is not here, but he helped us to put this whole presentation together. And I also like to thank NSERC, CNPq Brazil, and China Scholarship Council for the funding provided. And also Mr. Kashi, Guillermo Polit, and Reza Hesabi, who were collaborators in this project. I think we have some time for Q&A, but if you don't want to raise a question now, there's my email here on top right corner of the screen, rafaela.sanchez@mail.utoronto.ca. You can send a message to me there. And that's what I've prepared for today. Now I don't know if I should pass back to Amir or Danielle, but thank you everyone for watching.
I guess we have time for 5 minutes for question and then we'll wrap it up. If anybody has any question, just unmute yourself and just ask. Well, since there's no question, it's a lot of information to digest. So
yeah. Well, the papers has a few pages. I tried to condense as much as I could for this presentation. So yeah, it's a lot of information. So I highly recommend you to go through the paper and, you know, because there are a lot more details, a lot more information in there. And you can even find the preprint of this, which I'm allowed to share on my ResearchGate account. So if you can, or just Google the title and then you can also find it.
I will find it.
Yeah.
Well, thank you so much, Amir and Rafaela. And
Thank you.
I guess that's it for today. Everybody seems really happy, pleased with the presentation. So.
Oh, that's very good. Thank you, everyone.
Messages coming in, so okay.
Thank you very much, everybody.
Thank you, everyone.
Bye.
Bye.